Hi, everybody. Thanks for joining. I'm Paul Hillman with the Phased Array Group at Eddyfi Technologies. And today in this coffee break, I'm going to give a quick introduction to designing and carrying out inspection for components of complex profiles. I plan to highlight some of the tools available to make this a success in the powerful Ultravision 3D platform that we have. If you're watching this live, feel free to ask some questions as we go in the chat. I'll try to get to them at the end. Or if you're watching it afterwards, please send us a message and we'll surely come back to you. So in this quick coffee break today, I'm just going to talk about where we start with complex geometry inspection, what the challenge is, how we represent the part, designing and modeling of the inspection approach, and the analysis in a 3D environment. So what do I mean by complex geometries? For simple shapes like plate, butt welds, for pipes, beam path is relatively easily predicted, and ray tracing can be done in many software that's available out there on the market for these simple types of shapes, which are easily predictable. Now, for parts with changing geometry, particularly along a scan path, those parts that have non-parallel surfaces, complex curvatures, maybe on the top surface, on the back surface, it's more challenging to predict beam path, and indeed it will often change for every position along the scan length of an inspection. You can see here on the slide, the top view, a nominal 55-degree shear wave ray tracing. The beam is easy to predict where it will go. When we do the same thing on a complex profile like the saddle surface of a nozzle geometry, you can see there in an extreme case when the probe is at a 45-degree rotational position, if we do the same nominal 55-degree shear wave beam to that nozzle, we may never see that reflected back to the surface. So if there's in worst case scenarios, if there's a flaw in an area of interest there, the beam that's reflected back may not be returned in the right place. And you can see that represented by the red line. So it's important to consider the real geometry of the component when designing the inspection. The first step to accurately represent the parts you want to inspect. And for many parts, it can be parameterized. So where software will draw a part for you based on a few variables like thickness or weld geometries, vessel and pipe diameters, and things like that. For more complex parts that don't have rotosymmetrical or rotosymmetry, importing of the real CAD model that truly represents the geometry of the part can be much more beneficial. So here, as you see in the little video that played, we can import directly a 3D CAD model, and we use an SAT format, a common CAD format, to import the real profile of the part. And we can use that then for inspection technique design and analysis. Once we have the part accurately represented, we need to know how we go about detecting flaws in the region of interest that we want. So here's an example shown in the video of where we can insert, using the software of Ultravision, we can insert flaws into that model. We can position them, we can change the shape of them, the size of them, and the orientation of those flaws to represent what we want to find in the component and put them where we want to find it. And the flaw there you've seen is on one of the hooks in a turbine root, and in the root of a turbine blade. And we've positioned it to try and find a cracking that comes off of one of the hooks. With the software, we can also ask it to use that defect we've placed in the model and take away the material effectively of the CAD model, and thus it will act as a reflector when we're doing 3D ray tracing, so we can design and optimize beams that are reflected off of that flaw. It's also important to accurately model the probe and wedge conformity to the complex surface. With a pipe, normally the curvature is the same around the pipe, of course. Now with a complex part like this, the curvature can change, and we need to design a wedge that will conform well to the surface. So this type of software, allowing the wedge to conform and choosing how it conforms, can help us to do that. And there's a number of different scanners then that we can design in the software, because we really want to represent and simulate a scan path in the software that is as similar as or as close as possible to the real life path that the probe will follow on the surface of the part. So the example you saw in the video here is on the turbine blade again, and we're traveling across the aerofoil surface. And of course, the travel path across that surface is not the same as a straight line. And so we use what's called in the software a projected line scanner, where we project a line above the blade as a scanner fixture would be, and we ask it to draw a line along the surface profile. And that will be our scan axis, and that will be what's encoded during the inspection as well, so that when we come to do analysis, we plot the data in the right place. And that's just one of the type of scanners that we have. Of course, we also need to be able to place the probe in the right place on that 3D model as well, so it helps us to do that. There's other ones for normal XY scanners and pipe geometries and nozzles and others, but it helps us to accurately simulate as close as possible the real inspection scenario. Once we've got the defect and probe positioned in the model, we want to know where or what UT beam properties we want from the probe to detect the flaw that's of interest. So we can use a feature we have in the software, for example, here called minimize detection radius, where we postulate a beam. We can choose the wave mode and the number of legs and the minimum and maximum refracted angle that we want the software to consider, as well as minimum and maximum skew angle if we're using a matrix array probe. And we can ask the software to hunt for solutions to find the solution for the beam that gives us the best reflection back to the probe. And that's what we call the detection radius, shown there as the green sphere. So as close as possible back to the center of that sphere. So it tells us what angle we need. And in this case, it's a 61.6 degrees and a 3-degree skew angle, which we can create with a 2D matrix array probe with a shear wave wedge in this case. There's other things we can do from the defect side. We can create specular rays from that defect and have them travel back to the surface. And in that way, we can find a position on the surface that would give us the optimal position to find the indication as well. So we can work both ways, forwards and backwards. So if we figured out what kind of angles we want to cover for a particular probe position, it might be, of course, that along the scan path for our complex part, that the interaction of that beam with the area of interest will change because of a changing surface geometry. And here we can make use of coverage maps to build up a picture of those particular beams we're choosing. It might be the minimum maximum steering angle we want to draw, or a selection of beams across our aperture. You can see them here as different colors, so that we see the coverage of these along the scan length. In this case, the scan length is across a weld. We're showing upstream and downstream probes for a weld that has tapered profiles on the outside. Of course, then we go through the step of, once we've designed the inspection and done the calibration for our equipment, we gather the data using a range of different equipment. But when we come to the analysis stage, if it's a really complex part, we might want to consider analysis in the real 3D environment as well. So here in Ultravision 3D, we can plot the data back into the 3D model of the component, and we can combine 2D and 3D views. So we have the 2D UT data views you see on the left, a sector scan and a B scan in that case. And on the right-hand side, we're combining that with a 3D view of the nozzle in there, and also a cross-section view of the weld inside that nozzle. So these are what we call 3D slicing tools, because it's all good seeing an indication inside a 3D model like that. But if we want to do some sizing and accurate positioning characterization, it's useful to be able to slice that model as we please, and we can move the slicing around the nozzle here to see exactly where that flaw is inside the weld volume. So the combination of 3D tools as well and the 2D views. And what we do when we do the plotting of the data, the UT data into the 3D model, is we consider again the 3D ray tracing that you saw earlier. For each beam position, For each probe position on the surface, the software is going to calculate the trajectory of each beam and plot the indications as they would be, considering probe position, surface geometry, back wall geometry, any reflectors inside that part as well, which helps to make that a valid inspection. So in summary, in this quick presentation, I wanted to show you some of the tools that are available. Ultravision 3D is equipped with many advanced tools for design, inspection, and analysis of complex geometry components. It's useful to simulate the real surface profiles as they would be in real life, as close to true to life as possible. By postulating flaws, by adding indications and allowing them to be reflectors inside our model, it helps us to design an inspection with the right UT approach to optimize detection of flaws in challenging places. And plotting the data in the 3D view helps us to characterize and size as well flaws that are found in the data. And that's my quick overview. Of course, there's a lot of information to go through on this. We have some resources on the website. And if you have some questions, please let us know. And we'll be happy to answer those. There's a question here from Jonathan. Is Ultravision only compatible with Topaz data? Yes, today Ultravision is compatible with the data coming from Topaz instruments and also other Z-Tech instruments, the current Emerald platform, Dynaray, Zircon, Quartz systems. So these are compatible with this type of approach. Is it compatible with Gecko? No, not compatible with Gecko. If you need to use instruments creating the UV data files to design that. Of course, you can design your inspection in the 3D environment with Ultravision, figure out what setup you need, and then create that setup on a Gecko to carry out an inspection. The good thing about Ultravision is it can be end-to-end from design of inspection through to carrying out on one of the Ultravision-based platforms and to analysis in one single package. From Bradley, I'm looking for a better UT inspection system that is better than what we currently use. I work for the Air Force NDT Level 3 for the F-15 SPO, and we are currently using the USN 60 Epoch 650. Okay, these are conventional UT flaw detectors, both of these instruments. So single channel or conventional probes. The software I'm talking about today is around phase array, advanced phase array UT equipment. So we'd certainly be happy to help you look at moving inspections to phase array if that can bring you benefit. Is there a way to create a 3D model without CAD? Yes, it can be possible. If you don't have the CAD model or the 3D CAD model of the part you want to inspect in Ultravision, you can do a couple of things. You can import a 2D CAD, a DXF file, and extrude that. Maybe you rotate it to make a circular geometry, or you extrude it in X, Y, and Z component to make it longer in any dimension. So you can do that. You can also make your own, you can build 3D components from lines that you specify, lines and shapes within the software, which is, it can be done for some things. If you've got something really complex, it's better to have the 3D CAD for sure, but you can use those tools to draw something and extrude it yourself. And there's another tool for complex surface profiles that you can take a pin gauge, take the line from a surface, and import that into the software to draw a complex surface profile. Is Ultravision a paid program? Yes, sure. It's a complicated software, and it's you need a license for it, particularly the features I'm showing you. There is a free viewer for Ultravision Touch, so anybody can download Ultravision Touch and use the free viewer to open a data file, have a look. A lot of the advanced features I mentioned here, of course, are not in a free version, but you can open a UV data file and have a look at it with the UV Touch. Is it possible to use as an automatic inspection for Industry 4.0. I guess it can help. Sure, Industry 4.0, the buzzword for next generation data gathering and digital twinning and representing as true as possible a component. We can take the data we use for 3D to create imaging and show representations of the data gathered in a 3D component. It's not strictly, in my opinion, a digital twin for sure, because we're looking at just UT data rather than other variables in there, but it's certainly on the way to Industry 4.0, I would say. Is it possible to insert a 3D scanned equipment and use it inside Ultravision 3D? I think your question is probably around a surface profiler for gathering the net shape of something using photogrammetry or lasers. It can be possible for sure. As I said, the common format we use for importing into Ultravision is a SAT file. So if you were to gather a profile using one of these scanners, you would need to convert that in a standard CAD format into SAT format. You need to close the body of the model as well and make sure it fits some parameters to make it useful inside Ultravision. But it's possible. You could scan it, but you need to convert it to an SAT before you put it into Ultravision. How does the system compensate the changing curvature as we scan along the saddle surface, for example? Well, the system, we know the geometry surface. I think you're talking about nozzles because you mentioned saddle surface. So we know the surface profile because we have the CAD model inside there. And in fact, when we design an inspection for a nozzle, something with a saddle geometry, we take a step where we draw the beams that we want to be able to postulate using, for example, the coverage map I showed you going around the nozzle. And it's the case that when we go around the nozzle, the beams will skew as we travel around. So they'll be skewed the most by the geometry at the 45-degree position and come back to pointing dead at the center of the nozzle in the 0, 90, 180, 270 position. So what we have inside the software is a command we use to correct that skew and to tell us what skew we need to compensate for with the beams to be able to bring the beams back pointing to the center of the nozzle and therefore the weld fusion faces. And then the best approach we find is to use a 2D matrix array so that we electronically can create all of those skew angles as we go around the nozzle geometry to compensate for that. Thank you very much for your comment. That's the end of the questions, I think. So thank you very much for your attention. Feel free to send us your questions and see you all again soon.